All right. Now, let's look at the idea of the normal distribution. So the normal distribution is the general shape of the distribution of our statistics, of our sample proportion, p hat. Well, for a sample size that is large or large enough, okay, for large sample sizes, then the distribution becomes approximately normal. Okay? Now, this here is the mathematical model or the equation that produces the normal distribution. Okay? Now, that's important for Year 12 maths methods. Okay? But you can see the structure. You can see it's an exponential function, e to the power of, but in the power, you've got this bracketed term that is squared. So you've got like a quadratic of x. Okay? Gauss. 200 something years ago or more. Alright? This is called the Gaussian curve. Alright? Okay. So that's basically it's a very natural distribution. Okay? All measured quantities, if we measure, arm span of the population, all the variations in measurement of arm span, once you get enough of them and you look at the histogram or the distribution of them, it will be normal. Okay? Okay. Now what's important about the normal distribution is that we can measure its distribution with a center of mean and a standard deviation of spread. But the proportions of probabilities of obtaining certain values that are normally distributed, okay, has something to do with the amount of space you move away from the center. So if you move, say, one standard deviation width from the center, so this amount of space from there to there constitutes a certain percentage of probability. Okay? And so on. What do you think would be the total probability covering all possible values? 100%. So 100% of all possible values is the full scale of numbers. And then the chances of getting, say, a number way over here, which is an extreme number, if the expected value is, say, somewhere in the middle, then the chances of getting a number in your distribution way over here is very, very small chance. Maybe, 0.1%. Okay? What's the chance of getting a number that is the same as the mean? What is it? Half. Very good. A half, 50%. Because the mean is how much of the whole lot? A half. Yeah. So the chance of getting a value that is the same as the mean is 50-50. Okay? 50% chance. Alright, so we're going to now think about here. This is relating now to the distribution of one of our things we measured in our simulations. So you can see for population parameters of height, okay, when we got the measured quantities of height from our samples, we got our sample means, and so the distribution of all our sample means of height, as you can see, it really follows this normal curve. Okay, follows it quite well. Now we can examine the shape of our normal curve by changing two things. We can change the mean, okay, and we can change the standard deviation. So this quantity here is the mean. So if I change the mean, then if I decrease the mean, then the center moves down the scale, moves down the x number. So let's say my mean is 7. So then the center aligns with 7 on the x values. Okay? So the mean, changing the mean number is just a shift of the curve on the graph.
Is there a reason why it's always 0.1?
No, it's just this. That's just the increment that I've selected. Now, what about if I change the standard deviation? What do you think that's going to do to the graph? Wider or thinner. So if I increase my standard deviation, it becomes wider, but at the same time, it shrinks in height. What do you think it's trying to maintain? But as it gets wider, it has to squash in itself. What? Sorry, Karen?
The sample size.
Trying to maintain the sample size. Well, at this point in time, it doesn't know what the sample size is. It might be the population, okay? Because the population is also normally distributed, so it's very, very large. But if you widen something, then the height squashes down. So imagine you've got like rubber band, exactly right. Something fixed, like a rubber band or a rubber sheet. If you pull it, then the thing it's going to become thin. Yeah? If you try and squash it this way, then it kind of spreads out. So what's fixed about, say, this rubber band or rubber sheet? The area. Yes, the area. Okay? It's the same. Alright? The area is the same. So any material, this is not elastic enough, but you can say, well, this is a fixed, area, and if I stretch it this way, then it you can see from here, it kind of squishes up, doesn't it? Okay? Because it's trying to maintain the same area. Alright? So this is what the graph is doing. It's trying to maintain its same area. So if I decrease its standard deviation, that means I'm saying I want it to be thinner. It has to be taller as well at the same time because it's trying to maintain its same area. Now, the question is, how much do you think? What is the size of the area in units? What is the size of the area in units? I'll ask you another question. How do you find area under a graph? What's the calculus method we did to find area under the graph? What is it?
Integration.
Integration, very good. The antiderivative. Precisely right. The antiderivative or integration gives you the area. The gradient is the rate of change. So that looks at the steepness of the curve. All right. So let's ask that question. How much area do you think is underneath the curve? Well, what I'm going to do is I'm going to analyze the graph. I'm going to do the integral, okay, on the curve. So let's start with a lower bound, zoomed in to the camera. Hello. All right. So I'm going to select the lower bound way over here. I'm going to try and capture as much of the area as possible. And I'm going to highlight the whole area. What do you think that's going to go up to? Yeah. So there's not much area to measure at this proportion of the graph, is it? So it gets to 1, but then it just slowly gets closer and closer to 1. So it might be looking at the 5th decimal place, 6th decimal place, 7th decimal place, getting closer and closer to 1. All right? So you get a total area of 1 underneath your graph. What's that equivalent to? If you've got a total area of 1, starting from 0 and going over here to 1, then we're going to consider that the area underneath your curve is a model or a measure of probability. Okay? Because probabilities are an amount from 0 to 1, aren't they? So we use integration as a way of calculating the probability. Okay? So the area underneath the curve is equivalent to the probability of the distribution. Okay? So the calculus method is integration, and we got this very important way of calculating probability. So the big function f of x that we saw before, the Gaussian curve, okay? Well, if we integrate from, way over here in the nether regions, theoretically as far as negative infinity, all the way over here, and we integrate across, okay, up to some x number, where x is less than that number, maybe here, okay? And then that's saying, let's measure the area underneath the curve from way over here, which is hardly anything, but theoretically the curve just keeps going, up to some number. Then the area enclosed in that graph in that region gives us the probability of observing an x value equal to or less than that amount.
So does it ever touch the x-axis?
What's that?
Does it ever touch the x-axis?
No, because the graph theoretically, what happens, it's asymptotic along the x-axis. Okay? So this is how we find the area underneath the curve, and it's the same as evaluating the probability of observing a value from a normal distribution. Okay? So that's a very important idea. We're going to think about probabilities of normally distributed values, okay, in this way, as equivalent to the area beneath the bell curve. So here is 0.5 probability showing. Now 0.5 aligns to some value that is right in the center. What is that value that's right in the center? What do we call that? The mean. Very good. So the probability of observing the mean, or equal to the mean or less than the mean, okay, right up to the mean, is 50%. Okay? Alright, now let's think about the symmetries of all the curves and how the area is distributed. And that's very important. Yes, Lisa, question?
How come it never touches the x-axis?
Well, it's the behavior of the equation. This equation here, because, an important feature of an exponential function, okay, an important feature of the graph of an exponential function is an asymptote, isn't it? Alright, so if you've got an exponential function like e to the power of x squared, x squared graphs kind of have a turning point. They go up and then they turn and then they come down. So the Gaussian is a combination of a parabola mixed with an exponential function. It's got an asymptote, it rapidly increases, then it turns into a parabola and turns, and then it comes down and it goes down into an asymptote again. So it's like a combination of an exponential graph and a parabola mixed in. Creates this shape. Does that kind of make sense?
Wait, why does it still have an asymptote? Is it because the probability it can never be exact?
It's modeling the saying. It's saying, theoretically, we can measure the population of all the heights in the population, yeah, and on average, we've got some mean population, but there's some freaks out there. There's some 9-footers, yeah. Now they are the fringes of the population. They are the 0.001 percentiles of the population. They have values that exist way down here. Okay? Maybe one day we might get a 10-footer. He might be way down here. Maybe one day we might get a person who's 14 foot. They'll be way down here in the infinities. Yeah? So it's allowing for any possible value. Okay, because nature is very random. Nature is going to present to you the extremes. Okay? Does that make sense? Yeah. Alright. So let's consider how percentage or probability is distributed along the curve. So the way we measure the amount of probability that's distributed in our normal curve, we talk about amounts of a standard measure, okay? Like multiples of standard measure, okay? Just like when and it's like a unit of measurement. Just like when we measure distance, we say we've got meters or we've got feet, all right? How tall are we? Well, maybe we're 6'8" or something, 6 foot. So we say we've got multiples of feet, 1, 2, 3, 4, 5, 6 going up, okay? So when we talk about a distribution of probabilities in the curve, we talk about amounts of standard deviations. So we've got 1 standard deviation, 2 standard deviation, 3 standard deviation. Does that make sense? It's a unit of measure. Like we measure length with centimeters or meters or feet. We measure time in hours, days, things like that. Okay? So we're going to measure amounts of standard deviation from the mean. So there's your mean right in the center. If we measure 1 standard deviation, thump, that's maybe that large. Okay? 1 standard deviation on your normal distribution, 1 standard deviation from the mean gives you 34%. Okay? In probability, in area. Okay? So if you look at 1 standard deviation from either side of the mean, 1 standard deviation going this way, 1 standard deviation going that way, how much altogether? 68. Very good. 68. So the amount of standard deviations on either side of the mean we're going to work that out as a multiplier, Z. Z is your multiplier of how many standard deviations from the mean. So if we're going this way, we're adding on Z multiples of your standard deviation to increase your numbers, making it go up. Okay? So you start with your mean and you add on multiples of your standard deviation. That's what this is. If you're going down the number line, going smaller numbers, then you're subtracting multiples of standard deviation. Okay? Start at the mean and then you subtract 1 or 2 or 3 multiples of standard deviation. Okay? So let's try and measure from our graph approximately what kind of intervals we can form. Where if we've got a range of x numbers, okay, a range of x numbers such that our x is in between 1 standard deviation to the left of the mean, 1 standard deviation to the right of the mean. So that is starting at the mean, we subtract 1 standard deviation, brings us over here to this line. And then we add 1 standard deviation, brings us here to this line. So from there to there, how much area are we making up? 68. So it's just approximately 68%, depending on how accurate our distribution is. Now, what about 2 standard deviations? So if we go 2 standard deviations from the mean, so it's a 34, and here's another 14. Yeah? So it's 96 altogether, is it? Yep, 34 and 34 is 68. Add on another 14 and 14. So 68 and 28. It's 96. Very good. So we've just done 2 standard deviations from the mean, there to there. And you can see it's taking up the majority, isn't it? It's taking up the majority of the curve. Alright, now what about 3 standard deviations? 1, 2, 3.
What about the 1%?
Yep. So it's almost 100%, isn't it? Yep. It's actually, more accurately, 99.97. We've just got integer percentages here, but it's not exactly those amounts. So it's approximately 100%, as you can see. Alright? There's little bits left over, isn't there? There's a little bit here left over, and there's a little bit here left over after 3 standard deviations. Okay? Now, let's say that on our distribution we achieved maybe the most maximum number here, and on our simulation or measure of population we achieved the most minimum number here. Then we've got a range, and the range is the maximum minus the minimum. Okay? What is the size of the range similar to? How many? 6. Very good. 6 standard deviations. 1, 2, 3, 4, 5, 6. So the full range from the maximum to the minimum, the range of our distribution is approximately equivalent to 6 standard deviations. Yeah? Everyone see that? Because 3 standard deviations on either side from the center is approximately almost 100% of the whole lot of values. Okay? So one way of determining, if we had to estimate what is a standard deviation of our normal distribution, then you work out the range, and then you divide by 6. Does that make sense?
That's only for this particular graph, isn't it?
That's only for the normal distribution. Okay? It's, yep.
So what happens if you didn't want the standard deviation to be 6? So if it was 4, would you do range 5 and 4?
No. It is basically saying when data is normally distributed like, and it has this kind of shape, like we've observed, say, here. See how the actual experimental data we obtained in the simulation kind of follows this normal curve. Yeah? So then we've got a minimum here, and we've got a maximum here. Then we can work out the range, okay, by going, there it is. Your maximum is 178.7, the minimum is 165, so we get a range of 13.7. So if I go 13.7 divided by 6, I'm getting approximately 2.2. Okay? Does that make sense? Alright. Now, we're going to, what's important here is we can see intervals of values, intervals of x values, that's what we've described here. We can get intervals of different sizes, and an interval is formed by going by 1 or 2 standard deviations or 3 standard deviations from either side of the mean. Okay, doesn't have to be whole number multiples. You could have 1.6 standard deviations either side of the mean, and that will give you a specific probability. Okay, so it's important to see from a normal distributed data intervals of those values, okay, correspond to specific probabilities of observing them. Alright, so I might say, okay, I'm interested, what's the probability of observing normally distributed values between 10 and 20? Okay, well, you have to work out how many multiples of standard deviations from the mean is from 10 to 20. Okay, and then that has a specific probability. So let's relate that to confidence intervals. So there's an interval of x values. Okay, some multiple of a standard deviation greater than the mean or less than the mean. Okay? So, if a random variable x is normally distributed, comes from the bell curve, then known probabilities are associated with the interval, okay, of specific widths. So we might have 1 or 2 or 3 standard deviations from the mean. Those are the widths of our intervals. And we get specific probabilities because the shape is such that we can clearly define how much probability is 1 or 2 or 3 standard deviations from the mean. Now, a useful probability that is used to form specific intervals is 95%. Why? It's just an arbitrary amount. Okay? So, scientific literature, when they do research and they're trying to come up with, what is the optimum amount of push-ups you need to do to get fit? Maybe.
200.
What they do is that they don't come up with one number. Okay? They come up with an interval. They say, well, to get fit, you need to do around about 50 to 80 push-ups a day.
How much have you done?
And we're 95% confident that that is true. Okay? Why do they say 95% confidence? Well, there's no real reason. It's some dude who came up with the statistics said so. Alright? And it's a convention that statisticians and researchers in science and other fields have stuck to when they're forming, when they're reporting on their research.
People have never done push-ups in their life.
Okay? So it's an arbitrary amount that is convention in the fields of research. Does that make sense? Okay, it's like why does work start? Why do many jobs start work at 8:30? Why does school start at 8:30? I don't know. They just do. It's convention. It's tradition. Yeah. So some things in math and statistics are like that. 95%. It's basically saying okay, there's a little bit of leeway for error, but we're pretty good that we're capturing the majority of possibilities. 95% confident. Yeah. All right. So when we're talking about random variable x, okay, some value from a normal distribution can be found in such an interview, we say we're 95% confident that the value of interest is within that interval. Okay? We speak about the probability of observing that value as our level of confidence. We're 95% confident because there's a 95% chance that the true value of interest we're looking at is within this range. Okay? It's like if you're flipping a coin and I asked you, Josh, flip a coin, how confident are you that you're going to flip a head?
50%.
50% confident. That's correct. Okay?
100.
Because the chance of flipping a head is 50%. Alright? So, does that make sense? Yeah. Alright, so this is how we form confidence intervals like that. So this is the bracket notation. Alright? Where we have inequalities of less than, we use circle brackets as our thing. So we've got some value, some x value that's normally distributed, and that is an element of such an interval. And it's formed by that expression. So this expression of having multiples of standard deviations on either side of the mean. This here, when we subtract from the mean, that gives you the minimum value. When we add on top of the mean, that gives you the maximum value. So it's from the minimum to the maximum. Okay? Now the question is, maybe we can work out what is the mean, maybe we can work out what is the standard deviation from our survey, from our statistics, okay? But what is the Z multiple? What is the specific multiple of standard deviation that's going to correspond to precisely 95%? Okay? we had approximated values, we can see that 2 standard deviations is approximately equal to 96%. So if we want probability specifically to be 95%, is it going to be more than or less than 2? Less than 2. How much less than 2? Not much? Have a guess. What do you think the multiple value should be? 1.7? 1.87? Any other guesses? 94, 1.94? Any other guesses?
This is an auction.
Come on, we're starting probability. Place your bets. It's a gambler's choice. Any other guesses?
1.8.
1.8? What was yours?
1.9.
1.94? Any other guesses?
Who just wins?
All right, let's see what we will get. Now we're going to work out. We're going to do a little tricky math and work out what is this actual Z multiple number to get exactly 95%.